In this lecture, we're going to start talking about initial value problems. So, an initial value problem is going to be an ordinary differential equation that's paired with conditions that are imposed upon the unknown function y of x. So, if we think about first and second order initial value problems, they would look something like this. A first order would say solve dy dx equals f of xy subject to y of x naught equals y naught. And a second order would be something like solve the second derivative of y with respect to x is equal to f of x y prime subject to y of x naught equals y naught and y prime of x naught equals y1. The restraints that you see at the end of the problem, the subject to y of x naught equals y naught, y prime of x naught equals y1, those are called initial conditions. And those are what's going to help us go from a family of solutions to a particular solution. All right, so let's jump right in and do an example. So this time we have the first order initial value problem where we're given that y equals 1 over 1 plus c1 e to the negative x is the solution to the ODE y prime equals y minus y squared. So given that that's the solution, we want to find the solution to the initial value problem if we have the initial condition y of negative 1 equals 2. So for these problems, they've given you the ODE, but that's really extraneous information. We don't need that yet. In the future, we'll learn how to solve those ODEs, but right now we just want to work with that solution. So we're going to take the solution y equals 1 over 1 plus c1 e to the minus x, and we're going to plug in our initial condition to help us solve for that arbitrary constant c1. So if y of negative 1 is equal to 2, so if y of negative 1 is equal to 2, that means that y is equal to 2 and x is equal to negative 1. So we can plug those values into our solution to get 2 equals 1 over 1 plus c1 e to the negative 1. And we can simplify that to be 1 over 1 plus c1 e. Right? So now we want to solve this for c1. So we're going to multiply 1 plus c1e to the other side of the equation to get rid of our fraction. By doing that, we get 2 plus 2c1e is equal to 1. We want to get c1 by itself, so we'll subtract 2 from both sides. So 2c1e equals a negative 1. And then we'll divide both sides by 2e to get c1 by itself. So c1 is going to equal negative 1 divided by 2e. So we found out what value that arbitrary constant has to take in order to satisfy the initial condition. The last thing that we need to do is we need to plug that back into our solution. Because remember, these problems don't ask us to find the arbitrary constant. They ask us to find the solution to the IVP. So we're going to take that c1 value and we'll plug it back into the IVP. So we get 1 divided by 1 minus 1 over 2e times e to the minus x. Now, it's possible that this is going to be enough for your instructor because you've plugged this in, but if they want you to simplify it, we can go on, we can simplify this a little bit further just to make it look a little bit nicer. Typically we don't like to see a fraction within a fraction. So we can combine the e's that we see in the denominator there. So this is going to be 1 divided by 1 minus 1/2 e to the negative x, and the e that's in the denominator down here, we can write as e to the negative 1. So when we combine that together, we get e to the minus x minus 1. All right, so we'll find a common denominator down there in the bottom. The denominator would be 2, so that'd be 1 over 2 minus 1/2 e to the minus x minus 1. And so that'd be 1 over 2 minus e to the minus x minus 1 over 2. And then finally what we can do is we can take the reciprocal of the denominator. So that's going to give us 2 over 2 minus e to the negative x plus 1 if we factor the minus sign out. Right? So this is just a cleaned up version of the solution. If you are working a problem like this in your book and you check the examples and the answers in the back of the book, it'll probably look something like this. And so that'll be the solution to our initial value problem. All right, let's look at another example. So this is another first order initial value problem. This time we're given that y equals x cubed over 3 plus x squared plus x plus c is a solution to the ODE dy dx equals x plus 1 quantity squared. We want to find the solution if this is an IVP with the condition of y of 3 is equal to 15. All right, I'd like for you to take a moment and give this a try. So using the approach that we used in the previous example, see if you could figure out what the value of c would have to be in order to make this IVP work out. So pause the video and give it a try, and then resume the video once you have an answer. All right, so if we want to apply our initial condition, again, y of 3 equals 15, that means that y is 15 when x is 3. So we'll plug those values into the solution. So 15 will equal 3 cubed over 3 plus 3 squared plus 3 plus c. We can simplify these values. So first we'll simplify the exponents. So 15 is 27 over 3 plus 9 plus 3 plus c. And then we can combine those values on the right-hand side. So 27 over 3 is going to be 9. 9 plus 9 is 18. Plus 3 would give us 21. So 15 is 21 plus c. We'll subtract the 21 from both sides to get c is negative 6. And again, it's not enough just to find that value of c. You have to take that and plug it back into the solution to find your solution for the initial value problem. So we'll take y equals x cubed over 3 plus x squared plus x minus 6, and that'll be our solution for this initial value problem. Let's do one more example with initial value problems. This time we're looking at a second order initial value problem. So they say y is equal to c1 e to the minus x plus c2 e to the 2x is a solution to the differential equation, the second derivative of y with respect to x minus the first derivative of y with respect to x minus 2y is equal to 0. And they want us to find the solution to the initial value problem if y of 0 equals 2 and y prime of 0 equals negative 3. So notice we have two initial conditions this time, and typically when you're solving these problems, that's going to be the case. The number of initial conditions that you have should match the order of the differential equation you're dealing with. So we're going to use these two initial conditions to figure out what C1 and C2 are. So we'll apply our initial conditions. We start with y is equal to c1 e to the minus x plus c2 e to the 2x, and we plug in our initial condition, y of 0 equals 2. That's going to give us the equation 2 equals c1 e to the 0 plus c2 e to the 0. All right, if we go on to the derivative, we take the derivative y prime. That's going to be negative c1 e to the negative x plus 2c2 e to the 2x. And we apply the initial condition y prime of 0 equals negative 3. Then that'll give us the equation negative 3 equals negative c1 e to the 0 plus 2c2 e to the 0. So you can see by applying our two initial conditions, we arrive at a system of two equations with two unknowns. If we solve this system for c1 and c2, then that'll give us the values that we need to find the overall solution to our IVP. So we have this system of two equations, c1 plus c2 equals 2, and negative c1 plus 2c2 equals negative 3. So when you encounter a system of equations like this, you can use whichever method you're most comfortable with. So you can use elimination or substitution, Cramer's rule, matrices, whatever your favorite method is to solve a system of two equations with two unknowns. I'm going to use elimination. So I'm going to add the equations together. That's going to eliminate the c1 variables. So if I do that, I'm going to get 3c2 equals a negative 1. I'll divide both sides by 3 and get c2 equals negative 1/3. Now that I know that c2 is negative 1/3, I can plug that into one of my original equations. So c1 plus c2 is equal to 2, means that c1 plus a negative 1/3 has to equal 2. I'll add the 1/3 to both sides to get c1 is equal to 2 plus 1/3, or c1 is equal to 7/3. And again, once you know both of these values, the final step is to take them and plug them back into your solution. So this is going to give us the IVP solution of y equals 7/3 e to the minus x minus 1/3 e to the 2x. All right, when working with initial value problems, one of the things that we often worry about is the existence and the uniqueness of our solutions. When we talk about existence, we're asking ourselves, does the differential equation dy dx equals f of xy, does it possess solutions? So do solutions exist? And more specifically, for an initial value problem, do any of those solutions pass through our initial condition point, x naught, y naught? All right, if solutions exist, the next question that comes up is, are they unique? So by uniqueness, we're asking ourselves, when can we be certain that there is precisely one solution curve passing through that point x naught, y naught? Because it's possible that you can solve an initial value problem and you can come up with multiple solutions. And ideally, when we're solving these problems, we want to have one unique solution. So for example, here's an initial value problem that would result in multiple solutions. We have xy prime equals 2y with the initial condition y of 0 equals 0. If we go through the process of solving this, we'd find the solutions are y equals 0 and y equals x squared. And you can plug both of these into the differential equation and see that they both work. They both satisfy the differential equation. They both satisfy the initial condition. So there are two solutions to this initial value problem. We do have a theorem that will dictate when the existence of a unique solution would occur. And that theorem states, for the differential equation dy dx equals f of xy, let R be a rectangular region in the xy plane defined by a is less than or equal to x is less than or equal to b, c is less than or equal to y is less than or equal to d, and contains the point x naught, y naught in its interior. If f of xy and the partial derivative of f with respect to y are both continuous on R, then there will exist some interval I naught, defined to be x naught minus h to x naught plus h, where h is greater than 0, contained within AB, and a unique function y of x defined on that interior interval that is going to be a solution to the IVP. All right, so basically what we're worried about here with the existence of a unique solution are these two requirements. We need f of xy, and we need the partial of f with respect to y to be continuous. So if we can find a region where both of those statements are true, then we can guarantee that a unique solution exists on that region. So let's look at an example where we examine the existence and uniqueness of an initial value problem. So we want to determine a region in the xy plane where a unique solution whose graph passes through x naught, y naught would exist for the differential equation dy dx equals the square root of x times y. All right, so if we're looking at this problem, we know that f of xy is going to be the right-hand side, so that's the square root of x times y. And the first condition on our theorem is that f of xy has to be continuous. So when I'm looking at this function, the square root of x times y, in order for it to be continuous, whatever's underneath the radical is going to have to be positive. So that means that this will be continuous when x is greater than or equal to 0, or y is greater than or equal to 0. So if I multiply two positive numbers together, that'll give me a positive number, so that'll be fine underneath the radical. Alternatively, we could do x is less than or equal to 0, or y is less than or equal to 0, and get the same result. So there are two possibilities here to make sure that f is continuous. The second part of the theorem says that the partial derivative of f with respect to y has to be continuous as well. So if we rewrite f of xy as xy to the 1/2 power, remember we can always rewrite a square root as the 1/2 power, that'll make it a little bit easier to look at the partial derivative. So you should have learned about partial derivatives in Calculus 3. When you take a partial derivative, essentially you're going to use the derivative rules that you learned in Calculus 1, but you're going to treat any variable that's not the variable that you're taking the derivative with respect to as if it's a constant. So if I'm looking at the partial of f with respect to y, that means I'm going to treat everything that's not a y like it's a constant. So that x that we have inside, we're going to treat that x like it's a 5 or a 2. It's just a constant, right? So if we apply the power rule here, the 1/2 will come down to the front. We'll get xy inside, and then the power will become negative 1/2. And then the chain rule says multiply by the derivative of what's inside. So the derivative of what's inside would be x, so we'll multiply by x. All right, so this is going to give us 1/2 times 1 over the square root of xy times x, which we could simplify to be 1/2 times the square root of x over y. And then again, we can figure out the continuity. This will be continuous when x is greater than 0 and y is greater than 0, or when x is less than 0, y is less than 0. All right, this is a little bit more strict than the function f. Notice we don't have the equals to signs, and that's because we divided by xy right here. So with that xy being in the denominator, that means neither x nor y can be 0. They both have to be positive. All right, so when we compare the domain or the continuity of f with the domain or continuity of the partial derivative of f, we take the smallest subset, we compare them and we take whatever is smallest, right? So we reject the equal sign, we just take x is less than 0, y is less than 0, or x is greater than 0, y is greater than 0. All right, let's look at a second example with existence and uniqueness. So this time we want to determine a region in the xy plane where a unique solution whose graph passes through x naught, y naught will exist for the differential equation dy dx minus y is equal to x. The first thing that we're going to do in this problem is we're going to rewrite the differential equation so that it's in the proper form. Dy dx equals f of xy. So we'll add the y to the other side. So dy dx will equal x plus y. That means that f is x plus y. And so we can examine its continuity. That's always continuous. So it'll be continuous for all real numbers for x and for y. Next, we look at the second condition, the partial of f with respect to y. So if we do that, again, we treat everything like it's a constant if it's not a y. So when we take the derivative of x, that becomes 0. And the derivative of y with respect to itself will become 1. So the partial of f with respect to y is just going to be 1. 1 is a constant number, so it's continuous for all real numbers as well. All right, one final example for existence and uniqueness. This time, it's phrased a little bit differently. It says, does the theorem guarantee that y prime equals the square root of y squared minus 9 has a unique solution through the point negative 1, 1? Okay, so we're going to look at this problem. Y prime equals square root of y squared minus 9. So that means that f is going to be square root of y squared minus 9. All right, so the theorem will guarantee a solution through that point, negative 1, 1, if both f and the partial of f with respect to y are continuous at that point. So let's examine the continuity of the square root of y squared minus 9. So in order for that to be continuous, we need whatever's underneath the radical to be bigger than or equal to 0. So this will be continuous when y is bigger than or equal to 3. Right? If you say y squared minus 9 is greater than or equal to 0 and you solve, you'll get y squared is greater than or equal to 3. But in this problem, y is equal to 1. 1's not greater than or equal to 3. So the function will not exist when y equals 1, and that means the theorem fails. That doesn't mean that there's not a solution. It just means that the theorem doesn't guarantee a solution. The final thing that we're going to talk about in this section is boundary conditions. So sometimes when we're dealing with these will be boundary value problems. Sometimes when we're dealing with these problems, instead of having an initial condition where you have y and y prime both at the same value, you'll have a boundary condition where it gives you the constraint on one end of the problem as well as another end of the problem. So we just really quickly wanted to go over one of those as well. So we're told that y equals c1 cosine of 2x plus c2 sine of 2x is a two-parameter family of solutions for the second order ODE y double prime plus 4y is equal to 0. If possible, find a solution to the differential equation that satisfies the boundary conditions y of 0 equals 1, y prime of pi equals 5. So just like we did with the initial value problems, we're going to take those two restrictions, those two constraints, and we're going to apply them to our solution to see if we can figure out what C1 and C2 are. So if we start with y of 0 is equal to 1, that means that 1 is going to equal C1 cosine of 2 times 0 plus C2 times the sine of 2 times 0. Now the cosine of 0 is equal to 1, so we get C1 in our first term, and the sine of 0 is equal to 0, so the second term goes away. So we know now that C1 is going to equal 1. For our second restraint, we know that y prime of pi is equal to 5. So first we find y prime. That'll be negative 2 times C1 sine of 2x plus 2 times C2 cosine of 2x. And then we can apply our condition. So y prime of pi equals 5. That means when we plug pi in, we get 5 equals negative 2c1 times the sine of 2 pi plus 2 times c2 cosine of 2 pi. The sine of 2 pi is 0, so the first term will go away. And the cosine of 2 pi is equal to 1, so this is going to simplify to be 5 equals 2 times c2. If we divide both sides by 2, we get c2 equals 5 halves. So now we know that c1 is equal to 1, c2 is equal to 5 halves. Again, the last step is to take those two values and plug them into the solution. So we would get y equals cosine of 2x plus 5 halves times the sine of 2x as the solution to this boundary value problem.